Hello, my name is Curtis Scott. I'm going to be talking about blackouts today. My reference is a survey on power system blackout and cascading events, research motivations and challenges. I chose blackouts because I worked for 8 years in nuclear power, and everything from power generation to the electric grid have always interested me. And a blackout is a removal of that power that's generated, and I really want to learn more about how and why a blackout occurs. This is an actual picture of one of the nuclear power plants where I did my training and qualifications in New York. Also, I recently became a homeowner here in California, where, as we know, California is prone to a lot of blackouts due to harsh weather conditions and equipment failure due to earthquakes. This is why learning more about blackouts interested me. A blackout is a large-scale electrical service interruption that happens somewhere between the generation and the end user. So much of modern life relies on electrical power, and during a blackout, society can take a big hit socially, economically, and politically. This image shown is from the 2003 blackout, which I will discuss in a few slides. Due to the large geographical areas that a power grid covers, there's a high probability of facing different types of faults and failures. It's very hard to control the system if it spans over many states. Unpredictable faults and cascading events are what lead to blackouts. This table lists the major blackouts from 2011 to 2018. It shows the length of the power outage, the amount of people that were affected, and it lists the initial cause leading to the blackout. Some common causes are abnormal weather conditions like lightning, thunderstorm, high winds, transmission line failures due to trips or faults, cyber attacks, or transformer failures. One interesting fact that I learned is that a lot of times a transmission line failure or transformer failures are caused by animals. For example, one story I read about Kenya, listed 7 June 2016, there was 10 million people lost power for about 4 hours, and it was all due to a monkey falling onto a transformer, which caused it to trip. The subsequent uncontrolled events made the situation worse, and it led to a full system collapse. In order to maintain the power system stability, there are 3 very important properties that need to be controlled. Their frequency, voltage, and rotor angle of synchronous generating units. Power imbalances between demand and generation directly affect the frequency stability, whereas reactive power imbalances affects the voltage. Rotor angle behavior is a representation of the stability and synchronization of the whole system. When the system is subjected to an abnormal condition, such as sudden load reconnection, generator outage, or transmission line tripping, the subsequent instabilities must quickly be addressed. When they're not addressed, the system could lead to cascading events, which in turn most likely would lead to a blackout. There are protective features built into the system also. Power systems have built-in and operator-controlled protection features. UFLS, under frequency load shedding, and UVLS, under voltage load shedding, are one of the major ways that they initially tried to prevent cascading events from occurring. Load shedding means removing portions of the load in hopes to bring back balance to the demand and generation differences. They begin with non-vital loads to hopefully prevent further losses and to affect less people. The equipment itself has built-in protective features and also normal operating conditions that are designed to prevent damage or loss of equipment. The immediate actions of the operators are also key to preventing most cascading events. The most common protective plan is the one utilized by Western Electricity Coordinating Council, WECC. It was first developed in 1996, and it has since been updated to meet modern standards. The most severe blackout in the US-Canada grid was on August 14, 2003. The blackout occurred in the Eastern Interconnect. The Eastern Interconnect is shown here on the right. Here's how the event played out. There were reactive power issues noted leading up to the event. There were also software issues which led to the unavailability of the real-time system information. They used this real-time system information to help troubleshoot in real time to isolate sections of the grid, which could be helpful when trying to prevent cascading events from occurring. So without that, cascading events are likely. The first outage was in East Lake Unit 5. East Lake Unit 5 is in northern Ohio, which had been running under stressed reactive power conditions. And as I said before, reactive power imbalances affects the voltage. So in turn, this caused the voltage regulator to trip on overexcitation. While the operator tried to restore the voltage regulator, the unit ended up tripping, and cascading events followed, leading to a severe blackout. There were three 345 kilowatt transmission lines that tripped due to contact with a tree. This worsened the event and caused cascading transmission lines to trip due to being overloaded now that they had to take on the extra load from the loss of these three lines. And so they ended up tripping due to being overloaded at under voltage. From all this, frequency oscillations began, and it split the remaining grid into small islands, which led to an even greater blackout. The outcome of the blackout was that 50 million people were affected. More than 400 transmission lines ended up tripping. There were 531 generating units that tripped, and they estimated about 63 gigawatts of power was lost. This is an actual photo of the event, and you can see in the picture how dark the civilization is. The only light you see is from the lamps of the car. In the end, the task force on power outages reported the major cause was due to inadequate understanding of the system, lack of situational awareness, poorly maintained vegetation, and lack of support from the reliability coordinator. Table 4 shows the total number of blackouts recorded in the U.S. from 2008 to 2015. You can see it's a large number of outages each year. It's pretty consistent, over 2,500 on most cases. And each year, millions of people are affected. This causes a monetary loss of billions of dollars. Table 5 on the bottom pinpoints 2005 specifically, showing the duration of the outage. So the total duration was 175,000 minutes throughout the year. As you can see, the average number of people each outage is 3,700, with an average duration of 49 minutes without power. This pie chart shows the top 10 states that were affected by blackouts in 2015. As you can see, California makes up 25% of America's blackouts that year. And here, living in California, we see that a lot, and we're affected by that a lot. In the analysis, the major cause was weather conditions, and they saw a correlation between the states with the most abnormal weather conditions and the top states with blackouts. For instance, California, Texas, and New York. Cities and towns rely on electricity for many reasons. One in particular is to treat water for domestic use. Without this could pose a health risk in some countries and lead to disease or even death. Certain vaccines and drugs that require refrigeration are also affected. Hospitals depend on electricity for x-rays, ventilators, and theaters, which could cause danger to patients' life if lost. A lot of hospitals, or I'd say most hospitals, use backup generators, but this comes at a high cost and it's very expensive. They require continuous maintenance and testing to ensure that they're going to work upon a power outage, but it's a vital load, so it's needed. On top of all this, communications is affected because you lose telephones, you lose email. This flow chart kind of shows how each social, economic, and political is affected by a blackout. Socially, like I said, the road traffic's like we saw that picture earlier. The medical systems are affected. Economically, businesses are shut down. That takes a big hit. Politically, you're going to have political unrest for sure. That the civilians are not going to, be happy the longer this blackout occurs. In conclusion, electricity drives our way of life more than we know, and we don't realize its impact until we lose it. I know I haven't given much thought about blackouts before this, and I enjoyed learning about the how and why blackouts occur, because it's not something most people think about day to day. But having that extra bit of knowledge helps prepare us for when the next blackout comes. This knowledge is also needed as I start my electrical engineering career, and hopefully in the future we develop a better way to minimize or prevent cascading events and blackouts altogether. Thank you for listening. My name is Curtis Scott. Have a good day.